Jai Hind everyone. In this video, we will discuss regular grammars. So, when we talk about the regular grammar is generally a type 3 grammar. So regular grammar generates regular languages. Now, when we talk about the regular grammar, the production rules in the regular grammar have certain restrictions, and those restrictions are that they have a single non-terminal on the left hand side and on the right hand side consisting of a single terminal or a single non-terminal followed by a single terminal followed by a non-terminal. So, we can have a single terminal on the right hand side, or we can have single terminal along with a single non-terminal on the right hand side. So, this regular grammar is defined by J is equals to VTPS. So, this grammar is defined by the 4 tuples. The V represents the set of variables, or we can say the set of non-terminals. This T represents the set of terminals. So, in this terminals we can have alphabets, all the alphabets or the symbols along with this epsilon. Then P represents the set of productions, the production rules we will have for the regular grammar, and then S will represent the start symbol from where we are going to start that particular grammar, or the derivation of certain language for that grammar. So, there are certain types of rules we can have in this regular grammar, and when we talk about the regular grammars, generally regular grammars are represented in 2 ways. The first one is right regular grammar and the second one is left regular grammar. The thing in right regular grammar is we will in the production rules, either we will have a null production, or we will have a production in which on the right hand side we will have only single terminal, or we will have a production in which in the right hand side we will have a single terminal followed by a non-terminal. So, here A and B, they are the non-terminals, or we can also say them, call them as variables, where this small a is a terminal. Now, another representation for this regular grammar is left regular grammar. Now, in this left regular grammar, the rules are of this form, where, so you can see that these 2 rules are similar with right regular grammar. Now, when we are talking about this last rule, in which what we are having in the right hand side the non-terminal. First we are having the non-terminal, then we are having a terminal symbol. So, in this the terminal symbol is after the non-terminal, and in right regular grammar the terminal symbol is before the non-terminal symbol. So, this is just take a look at this example here. So, what we are having here, we are having certain productions, and let us discuss these productions. So, this S is your start symbol. Now, we can convert this S to small a S. So, this is the first production. Now, this is your OR symbol. So, basically here we are having 2 productions. So, you can write them separately. So, this S can produce AS and S can produce BA. So, these are the 2 production rules here, and we can alternatively we can also write them by placing OR symbol in between. So, this OR symbol is representing that S can produce small a S, or it can produce small b a. Now, again when we talk about these productions, we are having 2 productions here also. So, the first production here is A produces small c a, and this A again produces epsilon, or the empty string. So, this grammar is producing a certain language which is produced represented by regular expression A asterisk B C asterisk. So, let we check whether we can derive this particular regular expression from this regular grammar or not. So, suppose we are starting from this A. So, always we have to start from the start symbol or the start non-terminal. So, we are starting from this S, and S can be replaced by small a S. So, we are replacing this S with small a S. Now, this S will be replaced by this small a S. Now, recursively this S will be replaced by so many small a S's. So, this production we will apply this production number of times, and after number of times we will get a string where we will have similar number of A's. Now, how many number of A's can we have here? So, there is no limitation that how many times we can just use that production rule. So, we can say that there are let us say infinite number of A's here. So, we can have number of A's from 1 to infinite. So, we can represent that by A asterisk. So, we are having A asterisk S, and then now we are just replacing this S by small b A. So, now we are applying this second production rule, and now this A can be replaced by either CA or this epsilon. So, now first we are applying this production rule, and we are applying this production rule for a number of times, so that we will have a string, a number of A's followed by B, then a number of C's. So, after that we will have A. So, A can be dropped or A can be removed by applying this production rule. So, if we apply this production rule, in that case A will be dropped, and now we will have a number of A's, then B, then number of C's. So, how many number of A's can we have? Now, suppose what will be the minimum string can be generated by this particular grammar. So, we are suppose I am not applying this rule AS, I am directly applying this BA, and then for this A I am not applying this CA rule. Okay. So, I am just applying directly the fourth rule, where we are just producing, or we are just replacing A with epsilon. So, it will be small b. So, that will be the smallest string which can be generated by this grammar. So, this smallest string, now we are just taking a look at this smallest string, and this string where we are having a number of A's, then B, then number of C's. So, and we can represent that string by A asterisk, B, C asterisk, and the smallest string it is B. So, now what we know, that by this grammar we can generate a sequence or a string in which there will be any number of A's followed by B, then any number of C's. So, in the string at least there will be one B, but the number of A's before B, they can be from 0 to infinite, or the number of C's after B, they can be from 0 to infinite. So, the right regular grammar. Now, when we talk about the right regular grammar are more easier and general way to represent the regular grammars. Now, when we talk about the left regular grammar are little bit difficult, or they are not popular in the representation. So, when we talk about the right regular grammar, the regular grammar generates a regular language, and when we talk about the regular language, for each and every regular language there is a certain NFA. So, we can also say that for a right regular grammar there will be a equivalent NFA with epsilon. So, we are going to prove that. So, there are two directions. In two directions we can just solve that, or we can just show that. The first thing is, if the right regular grammar is given, so for that right regular grammar, just construct a NFA with epsilon that recognizes the same languages with the right regular grammar. Now, the second thing is, or the second way to show that is, if we are having a NFA with epsilon, now just construct a right regular grammar that describes the same language as with of the NFA. Now, suppose we are having a right regular grammar, and from that right regular grammar we are going to convert a NFA with null moves, or we can say NFA with epsilon. So, suppose that the regular grammar is just represented by this V sigma Rs, where this V is set of non-terminals, this sigma is a set of terminals, R represents the rules, the production rules, and S is your start state. Now, we are going to construct this NFA epsilon, which is represented by these 5 tuples, where this Q again the set of states, sigma set of alphabets, del represents the transition rules, and this S is a start state, and this F, this is your final state. Now, the set of states Q will be obtained by getting the union of V, the set of non-terminals, with F. F is the final state. So, this F basically is the new symbol which is denoting the final state. Now, the productions in R have 3 possible forms, and based on those 3 possible forms, we are going to add a certain transition. So, we are going to take a look at those productions. So, if the production is in the form of where we are just converting or we are just replacing this A with epsilon, then if A produces epsilon, then we are going to add, we will add a transition del A epsilon is equals to F. That means the A read epsilon and it will reach to final state. So, that transition will be of the form, suppose we are having this A state and we will reach to final state F by reading epsilon. The second type of rule is A produces small a, where we are having only one terminal at the right hand side. So, in that case, we will just add a transition del A small a is equals to F. So, that means if we are available at state A and at state A, if we are reading input small a, then we will reach to final state F. And for the third type of the production rule, where we are having a terminal followed by a non-terminal in the right side, we will add a transition del A small a is equals to B. So, it will be A, and on reading input A, we will reach to state B. So, by using these forms or these rules, we can create a NFA with epsilon for any right regular grammar. And the second way, if we are having a NFA epsilon, then by creating a right regular grammar from that. So, now we are having a NFA with epsilon, and which is represented by these 5 tuples, where this Q is a set of states, sigma is a set of input alphabets, and del the transition rules, Q0 start state, and F the set of final states. Now, we are going to construct the right regular grammar that will be represented by these 4 tuples. So, for each transition which is available in the NFA, that is del QIA is equals to QJ, we will construct the rule QI is equals to AQJ in R, in our production rules. Again, every state QI which is available in F, for that state we will add QI produces epsilon, this rule. So, suppose this QI is available in final state, in that case we will add this rule in our productions. So, these are the 2 ways to show that for a right regular grammar we are having equivalent NFA, or for a NFA we are having equivalent right regular grammar. So, just taking an example we have discussed before. So, what we are having 4 production rules here which are representing a grammar, and we have seen that this grammar is generating a sequence of A asterisk B C asterisk. Now, there is a first production S produces small a S. So, this production is of the form A produces small a B. The thing is, we are having same symbol A in place of this B. So, we can say that now our production rule is A produces small a. So, we are having this state A and we are reading input small a, and we are reaching to next state, and that is A again. So, for S, again for this production, we will create our transitions, and that transition will be on S, we will read input A and it will reach to state S itself. Then the second production rule, where S produces small b A. Now, by reading input B on state S, we will reach to state A. Now, at state A, we will have 2 more transitions, and the first transition A produces CA. We will read input C, and that by reading that input, the next state will be A itself. So again it will be a loop on A with input C. Then we will have this production rule, A produces epsilon. So if A produces epsilon, we will reach to final state. As we have discussed in previous slide, that for such kind of rules, we will draw a transition from A to final state F with epsilon. So that will be our NFA for that regular grammar. Now we can see that what regular expression or what regular language it is this automata is generating. So we can say that the minimum string is acceptable by this is B. Now before B we can have any number of A's, and after B we can have any number of C's. So it will be A asterisk B C asterisk. Now the second thing, if we are having a finite automata, then we can just transform that finite automata to write regular grammar or not. Now suppose we are having this DFA. Now in this DFA we can see that we are having two states, and so this Q for this DFA is containing Q0 and Q1, and sigma is having small a, small b. So for that and for that DFA, now the transition rules we are having. So we are just taking from the Q0, that is the initial state we are having. So if we are reading A to on Q0, then where we are going? We are reading A on Q0. Then the next state is Q1. So for that we are going to create a production rule, and that will be Q0 is equals to AQ1. Now here we are using this Q0, or we are representing this Q0 in capital case, or we can say the upper case. So and why is that? Because when we are just writing a grammar, then there is a basic convention that we generally represent the non-terminals in upper case, and we generally represent the terminals in lower case. So to distinguish between this what is terminal and what is non-terminal, we are using this Q0 in upper case and we are using this A in lower case. So the production rule will be Q0 is equals to small a Q1. The second transition on this Q0 is when we are reading B, that will be Q0 B is moving to Q0 itself. So at Q0, if we are reading B, then we are reaching to Q0. So we are going to add rule Q0 is equals to B Q0. So that is the rule we are having. Now for Q1, we are having certain transitions. So at Q1, if we are reading A, then we are moving to Q1 itself. So for that case, we are going to introduce the production rule for this transition, and that will be Q1 will produce small a Q1. And if we are at Q1 and if we are reading input B, then we will reach to Q0. So for that, we are going to add a production that Q1 is equals to small b Q0. So this is how we can just transform a DFA or a NFA to a right regular grammar. Now the left regular grammar. So we have discussed that what is the difference between right regular grammar and left regular grammar. So it can also be proved that the left regular grammar also produces the regular language, but it is not so straightforward. Now why it is not so straightforward? Actually left regular grammar produces a reverse of a language produced by a right regular grammar, in which we just reverse the rules. So suppose we are having this kind of rule, we just reverse that rule to this kind, and the set of reverse language of all regular languages is exactly the set of regular languages. So the left regular grammar produces the regular languages also. So, but to show that, what we have to do, first suppose we are having a left regular grammar, then first we have to just convert it to right regular grammar by reversing all the rules. So, what we are reversing here, you can see that we are reversing the right side of the production, where we are just converting this left regular, the production of left regular grammar to a production of right regular grammar. Now, after that, we will just create NFA for that with epsilon, and definitely that will create a certain string. And this is how we can just show that a left regular grammar is also generating a regular language. Now, whatever language we are just creating by this right regular grammar, or whatever language we are just created by a left regular grammar, they are having a inverse relation. So, suppose if left regular grammar is generating a string A B, at the same time the right regular grammar will generate a string B A. So, if you are taking this rule, let's suppose we are having small a tends to B A, and we are representing this B as small b. So, whatever the string, what the string will be, we will get from these production rules, we will get B A from these production rules. Now, I am just swapping this or changing this to this. So, what we will have? We will have A produces small a B, and let us say B will remain, the production rule for B will remain intact. So, we are not changing it. Now, the string we will get from this production rule is A B. So, after just converting this left regular grammar to right regular grammar, whatever string we are getting, that will be, or whatever language we are getting, that will be the reverse of the language which can be generated by this left regular grammar. So, at the time when we are just producing the NFA with epsilon, to find out the NFA for this left regular grammar, we have to just change or swap direction of every edge. So, we have to swap direction of each edge. So, in that case, we can get NFA for this left regular grammar. So, and when we talk about the decidability of regular languages, in that case, we know that if L is a regular language, then the transpose of this L or LT will also be a regular language. So, we can show that this left regular grammar will also generate a regular language. Now, we are having this example here. Now, these are the production rules we are having, and these production rules are of left regular grammar. Now, we can derive the ABC from this. So, how we can just derive the ABC from this? So, suppose first we are using this rule, the production rule for C, as we will start from C, and C can be rewritten as capital B C, and in this B, it can also be rewritten by this production rule, and it can be just derived to ABC, and in this A will be derived to small a. So, finally, we will have this small ABC string. Or we can also generate this recursively in reverse order, that again we are having this C to BC, then this B to AB, and this A to small a. So, first what we have to start, we have to start creating the string ABC from the right to left, but this is equivalent with the creating the reverse of CBA. Okay. So, let us understand this point. So, basically what we are going to do here, we are just creating the string ABC from right to left. Now, that will be same if we are creating the string CBA, which is reverse of this ABC from left to right, and then take the reverse of obtained string. So, if I am going to replace this, if I replace this C with small cb, that is the reverse of this rule, then we will replace this B with small b A, and that is the reverse of this rule, and then we will have this CBA, and after that we can just take a reverse of that, and so in that way we can generate a regular grammar or NFA for left regular grammar also. So, that's it for this lecture. In the next lecture we will just discuss the context free grammars. So, thank you.